So it's 2 past, so I'll start with the acknowledgement to country and introduction. So yeah, first let me begin with acknowledgement to country. So in the spirit of reconciliation, TMOS acknowledges the traditional custodians of country and their connections to land, sea, and community. We pay our respect to their eldest, past and present. So today's speaker is Professor Odom, who is a professor and chair of the chemistry department at Northwestern University. She is editor-in-chief at Nanoletters and member of the American Academy of Arts and Sciences and fellow of the Material Research Society, Royal Society of Chemistry, American Chemical Society, American Physical Society, and the Optical Society of America. She's a recipient of a huge number of awards, including the RSC Centenary Prize and the ACS National Award in Surface Science. Her work is focused on nanostructured nanoscale materials with exceptional properties. And these materials have applications in nanomedicine, nanolacing, photovoltaics, wetting, and imaging. And today she will talk to us about her work on nanoparticle plasmonic lattices. So thank you and welcome, Teri. And just before I hand over to you, so when people have questions, please feel free to enter them into the Q&A window during the seminar or raise your hand after the seminar and I'll chair the Q&A session as well. So thank you, Teri, and over to you.
Great. Well, thanks everyone for joining me this morning. I've been looking forward to sharing our work with the center, as well as finding new ways that we might collaborate, and excited about new ideas that can emerge. So thank you for hosting me. So I thought I would do is tell you a little bit about this platform that we have been using for a while, but it keeps surprising us. There are just many different things that these nanoparticle lattice can do, both collectively as well as what might be possible when we can control their surface chemistry and their surface materials. Before I go into that, however, I wanted to acknowledge the group, and this is a Zoom photo, of course, and we're also via Zoom, so we're making our way through the pandemic, but just also an acknowledgement that it hasn't been easy. And I'm grateful for the enthusiasm and the efforts of my students to stay positive, even as they've had their own challenges. So the work of the students that I will be talking to you about today are highlighted with these gold stars, a couple of postdocs, and a couple of excellent graduate students. So we've been interested in the concept of miniaturization of optical devices and components, very similar to the mission that TMOS has. I just thought I would show you a timeline of the physical structure and the advance that it has made to date to 2021. And so starting with these vertical cavity surface emitting lasers or VCSELs, where there is gain material sandwiched between 2 Bragg reflectors, a microdisc cavity. You can see that the size of the cavity is now starting to approach the wavelength of light that it can manipulate. And to get smaller, of course, we need to use metals, because metals can squeeze light in sub-wavelength volumes. But this is sort of the time scale. It actually hasn't been that long, about 40 years for miniaturization. And even in terms of the translation into technologies, there has been a significant advance in everyday devices, even in smartphones being able to use facial recognition to unlock your device. So there's a significant advantages in the miniaturization of lasers, as well as the building of optical components for compact systems. Another common device that the center is also focused on is how can we take some of the advances in bulk optics and translate them into flat optics that are more flexible and that are lighter and that actually can do different things. And so there's this challenge of having these bulk systems, and how can you then be miniaturized? And so this is a Fresnel-based structure of a lighthouse. And then recent work has shown that it's possible to mimic this these phase gradients using discrete nanostructures, usually dielectric structures. This is just one example. And also the ability of prisms to disperse white light instead of a bulky three-dimensional object. This can also be done in a very thin layer. These are metal systems on a surface. So the ability to actually structure things at the nanoscale and scale them has been driving many of these advances in optical device and component miniaturization. So in terms of plasmonics, or the ability of metal nanostructures to manipulate and squeeze light, I think it's more than just miniaturization, because if we take advantage of these metal-based components and how they manipulate light, there are many other things that can result. So just as a reminder, if light is shone on a metal nanoparticle, it will excite the conduction electrons, and they will oscillate around a center of mass in an electron cloud. And in this case, this is a dipolar excitation. And so what we'd like to do is take advantage of these localized fields around the particle surface and also exploit the intrinsic properties of plasmons. So if there's a head-to-head comparison against photonic properties, sometimes there's identified a disadvantage related to losses and quality factors. But in some of the work that I want to show you today, I want to make the case that it actually doesn't matter. What we want to do is to take advantage of these intrinsic properties and to maximize the potential in all aspects. And so what this means for us is that we can imagine new designs based on periodic flat optics. We have new mechanisms to manipulate light in the near field and the far field, and then also to achieve on-the-fly reversible tuning. Because of the intrinsic losses in the metals, they can be easily integrated into flexible substrates that can support a wide range of tunable properties. So this is the platform that I'm referring to, these plasmonic nanoparticle lattices, and the space that they operate on for us just seems to keep expanding and expanding. So if we just take a slice of this phase space, we can control the unit cell shape. These can be cylindrical or diamond-like shape, triangular-like shape. There's a range of different shapes that you can tune, and this controls the localized surface plasmon properties. We're able then to also control the lattice geometry, so they can be simple in terms of square lattices, or hexagonal lattices, Kagame lattices, honeycomb lattices, even super lattices or arrays of arrays. And then we also have the ability to tune along a different axis the materials. So there's a very broad space that we can operate in, from the UV all the way to the mid-infrared. Other lattice symmetries that we've been interested in are these moire type lattices, which these systems can actually do quite well. So this is the fundamental architecture, and then we'd like to integrate that with different types of emitters or different types of gain. And so just using this, building on the fundamentals that we understand on this lattice, we're able to achieve weak and strong coupling with this system. We are able to achieve enhanced emission of quantum emitters, and this is done in collaboration with Igor a while ago now. We're able to achieve, just starting with this periodic lattice, reconfigurable imaging by being able to control the local dielectric environment around the individual particles. And then we're also able to control these nanoscale lasing aspects. So today, based on some of the scope of work that's going on in the center, we'll be mostly focusing on the nanolasing and the imaging aspects. So as I mentioned earlier, these plasmonic particles, they can support collective oscillations, collective excitations, and this is a dipole emitter. If we take this same particle size and then we just put it together into an array, where the array spacing is a diffraction spacing, it's a photonic spacing, we can couple the localized surface plasmon and the diffractive mode. And that gives us a couple of different properties that are advantageous. If we look at the phase, we can see that we have a well-defined standing wave perpendicular to the dipolar direction. And then we also have very enhanced electromagnetic fields along the polarization. And on a particle by particle basis, the fields that are localized for the same particle in an array is about 2 orders of magnitude higher than it is in this case. And so what we gain is what we call these hybrid modes that have been commonly referred to in the literature as surface lattice resonances or lattice plasmons. And we take advantage of the photonic effects. So we are able to achieve high quality resonances. You can see that, for example, this 470 nanometer spacing, the line shape starts to approach, sub 5 nanometers. And then we also maintain these high local field enhancements. So we end up taking advantage of the best of both worlds. So this is an electron micrograph and an optical micrograph of what these lattices look like. These are just typical array parameters. So we typically pattern about a centimeter squared area. And these are some of the properties. So this is the SLR, this is normal incident transmission. This is the lattice interacting all together. You can see that the resonances are very narrow. And you can also see that these also support a localized surface plasmon resonance, and these are characteristic of particles, individual particles in the lattice. So it's really nice. You can take advantage of an individual particle property or the collective property of the array. And as you might expect, as you increase the refractive index around this array structure, then both of the resonances shift to longer wavelengths. So we can take these normal 0 order spectra and change the angle of incidence. What I showed you earlier was just a slice at theta equals 0. And then we can stitch them all together over very large angles, and we need large area samples to be able to do that. And we can construct the equivalent of optical band structures. And you can see that based on simulations, they match, they're amazingly consistent. And if we look at what's going on in the near field, right at this theta equals 0, or in the symmetry language, it's the gamma points of this lattice. Again, you can see these localized fields and this standing wave pattern. So we can control the short range and long range interactions. Okay, so I'd first like to discuss some of the advances that we've done in these particle lattices related to chemistry. Oops, sorry, it's come up at a different time. So this is a scheme of how we fabricate these particle arrays over large areas. We mostly start off with a floating metal mask, copper or gold. We dry it on a substrate that we want to fabricate the particles on. We deposit the material that we want. Then in the case of copper, we can etch it. In the case of gold, we can use Scotch tape to take it off. And in some cases, we can even just use a nitrogen blower to blow it off. So there's it comes off very, very easily, and then it leaves these particles. And so of course the particle arrays look quite nice in the Blender scheme, but they're different as fabricated. And so, for example, these as fabricated nanoparticles, they look pretty good, but there are the periodicity is perfect, but in terms of the individual shape, there is some variability because we're depositing through this whole array mask. So the idea is we take these as fabricated particles, can we thermally anneal them with a specific temperature time process. And then at the end of the process, we can reshape the particles so they reflow and then they solidify to form these dome-like structures. And so you can see just based on the tilted scanning electron micrograph that they look really, really nice though. So if we evaluate the crystal structure of these gold nanoparticles, we scrape them off with a razor blade onto a transmission electron micrograph grid. You can see that the surface is quite rough and the grains are small. You can see this in this the broadness of the fast Fourier transform. If we look at the annealed particles, you can see that the grains are much, much larger and the surface structure is quite smooth. And and I love this image here. You can see this is where the substrate was, and we have this beautiful hemispherical type shape. So if we evaluate the properties, we now start to get very narrow resonances that start to approach the theoretical limit. So for these as fabricated particles, the the full width hat max is not very impressive. And then in the annealed case, not only is the localized plasmon look nicer, but we have a reduction to 4 nanometers. And then after a month, it's also still very narrow. We can do the same thing for silver nanoparticle lattices. The full width hat max is a little bit nicer from the beginning, but after the annealing, the particle reshapes and the resonance becomes really narrow. And even after a month, the full width hat max remains narrow, even without having to protect the silver nanoparticles with an oxide. And for the aluminum nanoparticle lattices, we also get an improvement in the SLR. But as you can see by the cartoon, we have less reshaping of the aluminum, but the internal structure results in these larger grains. And so this is why we also get this reduction down to about 4 nanometers. So then we are trying to expand the toolkit based on materials. And then we are also interested in multiple functions. And so we focused on copper because copper is a really nice plasmonic material. It can also be directly integrated with electronic devices. And if we look at the Drude model parameters, they're very similar to gold. But the other advantage of copper is that it can function as a catalytic material. And in terms of this, it's very good for nucleating the growth of graphene. And so there's literature precedent on using chemical vapor deposition and methane as a source and hydrogen as part of the reductant. And part of the reason we wanted to grow graphene is, well, we wanted to see whether we could conformally coat the particles, but also it would mitigate this effect related to copper surface oxidation. Because once the copper comes out of the chamber, it immediately forms an oxide and is not self-limiting. It's more similar to silver in this way, and the quality of the resonance is compromised. So we carried out CVD synthesis using these components for the conditions. And then we had to use a relatively high vapor pressure to make sure that all of the copper didn't evaporate, because we're still operating at relatively high temperatures, 900 degrees. And so we needed to be at these high pressure, relatively high pressures. So these are what the as fabricated copper nanoparticles look like. They're not annealed. You can see that there's still rough edges, but the sizes are quite good. After we grow the graphene around the copper, you can see, because of the heating effects, that there's we have this dome-like structure, but they look good. And then to ensure the uniformity and conformality of the graphene, we evaluated the transmission electron, used transmission electron microscopy. And so you can see few layer graphene that's on the particles. You can see where if we scrape off the particles, there's only few layer graphene on the top, not the bottom. We used XPS to ensure that, or to test whether the particles would oxidize. And you can see these dominant copper peaks, and they look good. Where the oxide peaks would form, the copper oxide peaks would form right around here, 945, and a little bit here at lower binding energies. So there might be a little bit if you squint hard enough, but for the most part, the copper does a really nice job of covering the surface. So just to compare what the linear optical properties look like, for these are calculated for copper and the copper that is coated with graphene. And you can see that the experiment matches quite nicely. But moreover, we have this really beautiful, sharp, and deep SLR from this hybrid system, this core shell copper system. After a week, the full width hat max is still narrow, and after a month, it still remains narrow, even after being in an ambient conditions. So these are the narrowest SLRs to date, especially at visible wavelengths. As you go farther and farther to longer wavelengths, it's easier to achieve these near resonances, just mostly based on the properties of the metal. But in this case, at these visible wavelengths, this is very exciting for us. Okay, so in terms of applications, the first one that I'll focus on is nanoscale lasing. And we need to be able to overcome the diffraction limit, which is limited for dielectric materials, but is not for plasmonic materials. And so this idea, or the conception, was started by Mark Stockman over 20 years ago. And the idea of a spacer was there would be a thin metal shell surrounded by quantum dots as gain. And so you can see what the evolution of the architectures have been over the past 15 to 20 years. And today we're going to be focusing on this nanoparticle array. So the way that these arrays work as a nanoscale cavity is that we build the array and then we surround it with gain. So the gain can be in a solid matrix or a liquid matrix, but the liquid matrix is quite nice for some tunability purposes. We then pump the gain, and then the gain will transfer its energy to the nanoparticles. And this molecule is IR140, which is a common laser type. So this is where the position of the lattice mode is, or the SLR. And this is the photoluminescence gain bandwidth. And so wherever the SLR mode is, wherever the cavity mode is, that is where the lasing wavelength emits. So we can tune this SLR anywhere within this IR140 bandwidth, and we'll achieve lasing at that particular wavelength. So it's very, very tunable. So we're able to achieve single mode emission sort of by design. There's a very high local optical density of states. This is at the gamma. This is from the gamma points coming normal to the surface. The 9 widths are quite narrow. There's a clear threshold with a nonlinear increase in intensity. We have a beam that we can manipulate in the far field, and the divergence is quite low. And one feature that I really appreciate about this system is that the mechanism is a deep subwavelength one, meaning this is a spatial map of the stimulated emission rate term. And so you can see that only molecules that are within the vicinity of the hotspots contribute to population inversion. So only the molecules that come in and out of the hotspots here, which I think is pretty amazing, and also takes advantage of the plasmonic-based metal properties. Okay, so if we try to take advantage of these nanoparticle lattices that now have graphene around them, and this is what the cartoon looks like, and this is the optical micrograph of what the array structure looks like. It looks quite nice. We start off with the cavity mode, which is a very high quality. It's already 2 nanometers full width half max. And then we are able to achieve lasing at this SLR wavelength. And the lasing width, line width, is less than 0.2 nanometers. I expect it is actually less than this, but that's just the limit of the spectrometer, which is pretty nice. It comes off as a beam and as a spot, and there's a slight difference in the nonlinear and the thresholds of whether it's just copper or whether there's graphene around copper. But in general, it's a very nice system. Okay, so what other lasing characteristics can we feature that highlight the flexibility of this system? The first one is we can mechanically tune the wavelength of emission by patterning these gold nanoparticles onto polydimethyl siloxane, which is an elastomer, and you can apply in-plane strain. If you apply in-plane strain, the distance between the particles increases, which is why the wavelength of lasing increases. And this is where the advantage of having liquid gain comes in. So even as you're stretching the solid substrate, the liquid can always be surrounding the metal nanoparticles. So molecules are always in the hot spots that can be used for lasing, which is sort of a nice system. Another example is this polarization dependent dual mode lasing. So in this case, we have a different type of lattice structure, which I'll explain more in just a minute, but we have these interesting shapes of the unit cells that have polarization dependence, so we can get different colors out depending upon the polarization. And then finally, here's an examples of super lattices or lattices of lattices. And so we have these super lattice SLRs, and each of these can show emission at angles that are off normal. So this one comes off at normal, but these at these different wave vectors at these different band edge modes supported by the that super lattice supports can also show lacing. So it's quite nice. But I will just focus on the middle case just to start. Okay, so in this type of geometry, these are the basis vectors. These are aluminum nanoparticle lattices. If the polarization is in this direction, you notice that there are two SLRs at two different wavelengths, and these are coming from different coupling to different Bragg modes. So either the 0-1 mode, 1-0, these are degenerate at this point, or a 1-1 mode. And so if we look at the phase maps, we can see that at the shorter wavelength, you have a standing wave mode in this direction as you, that corresponds to this. We just changed the basis, we just rotated the basis. And in this case, you have a standing wave mode in this direction according to the 1-1. But what's interesting is that if we look at the hotspots at these same locations, at these different wavelengths, so λ1, the shorter wavelength, λ2, the longer wavelength, they are in the same positions for the rhombohedral particles, these diamond-shaped particles. So they have overlapped hotspots. So the hotspots are in the same positions along the short axis, but at different wavelengths. This is quite interesting. And I'll show you the outcomes of that in just a minute. But you'll notice that if we keep the lattice the same, but have the unit cell be symmetrical, that the fields will go along with the polarization. So here we've forced the hotspots to remain where we want them. So we can use this system to test for lasing, and we're able to achieve dual mode lasing. This is the gain bandwidth, the C481. This is the photoluminescence, and these are the wavelengths of the lasing modes that correspond to the SLR wavelengths. And you can see that it spans pretty well the whole bandwidth. We look at the light curves, thresholds are about the same, which would make sense. And then this is the simulated spectra that I showed you earlier. And again, this is the stimulated emission map. And so you can see that regardless if we're evaluating lasing at shorter wavelengths or at longer wavelengths, and again, these are a function of polarization, the hotspots are always at the same locations. So you have different molecules, but in the same hotspots that can contribute to these different colors, which I think is quite interesting and unique to think about engineering at the unit level and breaking symmetry in order to access these types of properties. And so we thought about, okay, so this is all in a single lattice and change the unit cells. That helps quite a bit. But because we have these really large areas of samples, can we design sort of macro scale devices and start putting them together in interesting ways? And so one of our goals was to achieve white light emission. And so we designed this sandwich structure of two different lattices that are facing each other. And again, these are aluminum nanoparticle lattices. We focused on a spacing of 450 because the 450 nanometer spacing produces these two modes, very similar to what I showed you earlier. And then we also focused on a lattice that was 350 nanometers because that was able to support an SLR that was in between these other SLR modes. So then the question became, what types of emitters can we couple with these systems? So there were two different types of dye molecules that we used to couple with this 450 nanometer lattice. So we used C480 for the shorter wavelength emission, and we used DCM for this longer wavelength emission. And then for this green emission, we used C500. And so if we just look at evaluate separately each of these lattices combined with the dyes, we see this really nice red lasing, green lasing, and then blue lasing from these substrates. But then what we'd like to do is to be able to control the color of the lasing by starting to change the dye ratio. So these are empirically determined concentrations. So we add 3 millimole of DCM to 20 millimole of C480, and then we have a blue pump. And then by controlling the volume ratio, we're able to achieve different relative intensities of emission from the dyes, lasing emission. And so the color that comes out is this integrated color of blue and purple. Okay, then we decided, well, can we put these, now can we sandwich these lattices together, and what do their properties look like? The bottom lattice and the top lattice have different lattice spacings, the same ones that I introduced earlier. And you can see that regardless of the twist angle, if you will, in terms of the linear optical properties, they remain the same. So they look nice. You see these 3 SLRs. And if we look at what the modes look like, this is the dispersion diagram. You can see this is the gamma point here for the red SLR, gamma point for the green, and the gamma point for the blue SLR. So then we decided to start having these substrate, or these 2 sandwich substrates, and then mixing dyes in the interior. So first, let's focus on the DCM added to C500. And again, you can see by controlling the volume ratios, then you can have higher intensity lasing emission at shorter wavelengths or higher intensity lasing emission at longer wavelengths. If we combine C480 with C500, you can see everything shifts to bluer wavelengths here, bluish greenish wavelengths. And then again, by controlling the dye volume ratio, we can get different intensities of color. This is pretty neat. And then finally, these are all these data points that we have collected, some that I already showed you. So we're interested in this in the CIE plot in the center. And so we're able to, by this empirically determined volume ratio, we're able to achieve these relative intensities. That was the closest that we could do for white light. So if we integrate in this collection angle, this is what we get. So I think this is pretty neat. It highlights a number of different things. You take advantage of that you have large areas. You take advantage of that you can, that some of these symmetry properties are, I don't want to say protected, but they're invariant to how you change different types of parameters. And then because these dye gain is in solution, you can do, you can mix and match. Okay, so that's all in liquid. But of course, there are advantages towards solid gain. And the 2 advantages that I want to highlight are related to polarization control as well as directionality. So these ideas of shaping light based on polarization, phase, and intensity, they're important for microscopy, lithography, optical trapping, some quantum encryption applications. And so, but basically at the end of the day, we need these compact light sources. So the first system that I want to show you or introduce are these up-conversion nanoparticles. And so we're going to combine them with a silver nanoparticle array. And then this is the Jablonski diagram and the energy transfer that's expected, where you have a sensitizer, which is ytterbium, and an emitter, which is erbium. So we pump with longer wavelength light and we get out shorter wavelength. So this is the up conversion. And so the idea is, can you design a plasmon resonance that can overlap in energy with one of these transitions in these manifolds? So we'd like to be able to achieve single mode up converting lasing out of all of these different types of emission pathways. And let's see. And also if this can be plasmon enhanced. So if we just consider a slab of up conversion nanoparticles, you can see that there is more or less uniform increase for these different electronic transitions as a function of pump power. And if we look at this on a log plot, you can see that the slope is about 2. So that's the 2 photon process involved, and it reduces at very high pump powers because of saturation effects. And so if we evaluate these upconversion nanoparticles on the lattice, you can see, unlike the case where you just have the upconversion nanoparticles alone, as you increase the pump power, you have selective increase of one of these modes. And moreover, this is a single mode upconversion under a continuous wave pump, so it's not pulse, so it's continuous wave. And then if you look at the log plot, you can see, okay, we have a little over a 2 photon process, and then it becomes very nonlinear during the lasing regime, and then it tapers off just a little bit. But if we evaluate this threshold, and we have one that's even 3 or 4 times lower, this is already 2 orders of magnitude lower than semiconducting diodes, commercial semiconducting diodes. So this is quite nice. It's a little bit unexpected that it's so low, and that it can be excited under a continuous wave pump. But it indicates, and the mechanism is quite interesting as well, but it indicates that even in these unconventional materials, we can start to achieve metrics that are important for translation. Another common nanoscale emitter are colloidal quantum dots. So we worked with Ted Sargent, who supplied us with these biaxially strained quantum dots. This is what the scheme of the system looks like. And again, these are these large areas that we have. The transmission electron micrograph looks quite nice. And this is the nanoparticle array. And you'll notice that there are a couple of different resonances here. So this is the photoluminescence in blue of the quantum dot emission, and we achieve lasing in the middle of it, but it's due to what is called a waveguide SLR. And the reason why we have these new types of hybrid modes is that the colloidal nanoparticle film has a relatively high index. So we no longer have a pure SLR, but we have an SLR hybridized with a waveguide. This is waveguide TM, waveguide TE mode. And so we're interested in looking at what the polarization properties of the emission looks like. And so we see first establishing the log on a log-log scale, what the input-output curve looks like. And different from the dye molecules, you can see this is this characteristic S shape as you would expect for semiconductors. But it looks nice. And then when we looked on the beam profile, what the beam looks like, I mean, this sort of came out at the same time as the discovery of what a black hole looks like, even with some of the intensity differences. I mean, so it was surprising to us why there was nothing in the middle, but then there was some brightness at the edges. And so we put a polarizer before the detector, and then we found that the intensity changed and the location of the spots rotated as we changed the polarization. And so we know from these polarization patterns that this is a radially polarized emission, which is quite interesting and quite nice. We can also change the thickness. So in this case, we reduced the thickness of the quantum dot film. So instead of coupling to the waveguide TM SLR mode, we're coupling to the waveguide TE SLR mode. And so that's what happens here. And then we also get this nice narrow emission. And different from the TM SLR mode, we now have azimuthally polarized beams. And so we are able to achieve either radially polarized or azimuthally polarized lasing simply by changing the quantum dot film thickness. And that relies on what is providing the feedback based on these, where the energy of the emission of the quantum dot intersects these modes used for lasing. And we can also use this type of system to achieve directional lasing. And so this is the system in this case with a PDMS on top. And we use these core shell with very large shells. And the shells usually do not provide enough gain and that's why mostly the emission is from the core. But if you pump hard enough, you can see gain from both. And so we use this system. Sorry, neither my mouse nor my cursor is working quite well. And so we were aiming for emission at still a high symmetry point, the gamma point, and these are these high symmetry directions of a square lattice. And so the delta point converts to about 19 degrees. And so this is what the pump looks like. These are what these 4 lasing spots, and this is the cartoon of what the emission properties look like. And we're able to achieve 4 azimuthally polarized lasing beams near the delta points. These are all about 19 degrees from the center. And so this is pretty neat, and we can also just test the beam profile characteristics again. Okay, so moving on to other types of optical devices and components, I wanted to focus a little bit, just briefly, on lensing before I finish up with the photocatalysis. And so it's nice to these reconfigurable lenses. You can stretch them, and then you can change the location of their focal distance. The challenge with this type of the metasurface design, of course, is that you lack element-wise control. And actually, the focal position is like super spread out. It's not that confined, but it does a nice proof of principle. There's also been some history and these phase change materials using laser writing techniques. And there's a significant advantage in this case because you can tune at the single unit level. But there are, again, some challenges related to serial writing being non-scalable and also being limited to the infrared. Okay, so the idea that we had is to design what we call lattice lenses. We're still going to use this concept of discrete grid, where the properties are given by the size of this as well as the transmission at each point. So you can have transmission through or not through any given position. But of course, this is problematic related to how are you going to design even a simple 10 by 10 lens. There's too many possibilities for focusing. And then if it's also a design challenge because the brute force calculations will be way too long, way more than the age of the universe. So the idea is, can we use genetic algorithms to help us where we convert all of these to binary? So we have a single DNA strand, which is 1,089 bases. And then we can run a lattice evolutionary algorithm. This is a home-built algorithm that we designed. And this is the population numbers that we started with, where the fitness function was related to the intensity at the focal point, normalized by the distance from the maximum to the focal point. If we don't have this denominator, then we get these instabilities. Okay, and this can happen pretty quickly for a simple design. So then we extended this from whole arrays to these nanoparticle arrays, because the nanoparticles support these localized plasmon resonances. And if we control the shape of these, we can control the operating wavelength. But then, of course, it became more complicated because we need to use finite difference time domain simulations. So we had this inverse design where we used a black box approach and a multi-objective optimization. So it's not simple, and it sort of took a lot of time, but at the end of the day, you can get imaging or actually focusing at 3 different colors of wavelengths, each of them defined by the localized surface plasmon of the particles. So then we wanted to do a little bit better and to take advantage of these SLRs that I mentioned earlier, but let's just see if we can locally pattern the dielectric. Because if we do, we're able to control the wavefront just by shaping the patterns, just by shaping the dielectric patterns. So for example, if it's surrounded by PMMA, which is index matched to the substrate, you're going to have light that's scattered in plane, and so no light is going to be transmitted. However, if there's just air around the particles, because of this index mismatch, you don't excite the SLR and it just goes straight through. And so this is the similar idea. And so this is what the pattern substrate looks like. We first started out with electron beam lithography because it was easier to pattern elements by element. And you can see that it's easy, very easy and straightforward to control the focal point. We then tried to achieve multifocal point lenses. And so this is also possible. This is in the same XZ position, different displacement in X. These are in 3 different locations in X, Y, and Z. And also we can control the number of focal points. Having 5 focal points is computationally a little bit expensive though. But we were interested in the scalability of these structures. So what we wanted to do is to reconfigure arrays of lenses all at the same time. So we use this approach called solvent-assisted nanoscale embossing. We start off with these lens arrays in silicon. We mold these soft masks, which will transfer this pattern onto the lattice. And then this is what we get in terms of these SU8 patches. So all of these meta lenses, these patches are still on top of the plasmonic array. So we can take this mold, and then we can wet it with solvents and put these different patterns, results in these different patterns up for drying. We can then take a different mask, wet it with solvent, and retake all of this polymer for the 4 focal point lenses, and then make 3 focal point lenses. And then this process can be just repeated. So you're not removing any material, any dielectrics, you're just manipulating all the material at the same time. And so back and forth, you can see what happens. You go from 4 focal point to 3, to 4, to 3, to 4. So it's quite nice. We wanted to do some very simple imaging. So we're able to form a single object imaging. We're able to do multi-object imaging. This is all in the same plane, but again, we're still limited to diffraction. But in terms of some other properties, and this takes advantage of these transparent flexible substrates, is we are able to achieve single plane imaging. And then we use the same substrate and just again do sane, and then we can achieve multi-plane imaging. And so this is for NU. This is what it looks like for a single focal point lens, and this is the image. And then of course, in these different multifocal point lenses, these images appear in different magnifications. And then again, this is another example of this on-demand image tuning. Look at the single focal point, we do our sane, we can get 2 focal points, then we can get 4 focal points. It's quite robust. Okay, so in the last 5 minutes or so, I just want to deviate a little bit from some of this, these optical advances to expand what I call this MetaOptics platform. And it builds on the functionality of copper. So we can design these copper, and now instead of graphene, surrounded by platinum. And so platinum is a good catalyst for hydrogen evolution reactions. And because these copper nanoparticles support these really nice near fields, we'd like to take advantage of light harvesting and catalytic properties. So in this case, we start off with these lattices, and then we put them into a solution to start seeding and growing this platinum shell. And we can model the displacement and diffusion growth. It's fairly straightforward and consistent with what we expect based on the reduction. And so we do get some of these shapes that happen because these are edges that will start to etch in the very beginning. And so the SEM images look reasonable. These TEM images, you can see again the shape. And if we look at the elemental maps, you can see that there's copper throughout the particle, and platinum is mostly confined to the core layer. So we initially wanted to test just the photocatalytic properties of these arrays, but we found out we didn't have enough sensitivity in our detector to measure the hydrogen that was being evolved. So then we decided to measure the photo-electrocatalytic properties. So what this meant is we needed to put these arrays on a conducting substrate. And in this case, we put them on indium tin oxide because it's conducting and transparent, but it also has a high index. And so we needed to do some modeling to be able to see where do the resonances of the SLR occur, where is the localized surface plasmon, and where are these interband transitions. So these are at different wavelength ranges, longer wavelength for the SLR, redder for the LSP, and these interband transitions are green wavelengths, but you can see that the intensities are orders of magnitude different. So then we tested this photo-electrocatalysis under white light. This is the electrochemistry setup in a neutral pH. And you can see if we compare the current density versus potential for copper nanoparticles, platinum, and then the ones with the core shell particles, that if you change the intensity of the white light, that the copper nanoparticles and the copper core shell with platinum nanoparticles, they depend on intensity. So that makes sense. The localized, the plasmonic aspects are functioning quite well. But if you look at the platinum case, there's no effect. We then wanted to compare the plasmon modes in terms of the SLR, localized surface plasmon, and the interband transition. So we put a filter out so we could test the effects of different excitation wavelengths. So we have a long pass filter at 830, so we can test the SLR, a long pass and short pass, so we can test mostly the localized surface plasmon, and then a short pass. And so you can see if we compare these, again, current densities versus the light intensity, and this is just decomposed into where there's no light on, the white light that I showed you in the previous slide, and then these different wavelength comparisons, that there's a more significant increase if we look at these red curves here, which correspond to the SLR. And so it's about two times higher than that from just the localized surface plasmon itself. So there is a distinct advantage to having these SLRs. Okay, so in summary, I've tried to introduce this nanoparticle platform where you can do chemistry, you can anneal them to achieve narrower resonances, and then if your plasmonic material is catalytic, you can even grow things like graphene. I introduced nanoscale lasing with the solid state quantum emitters. We're able to achieve continuous wave emission as well as polarization and directional control. We dabbled a little bit in the design of flat lenses and to be able to tune them with all these interesting properties that would be very difficult to do if we just used analytical expressions. And then finally, I think it is a quite powerful platform for a whole range of light matter interactions. I mentioned briefly just photo-electrocatalysis, but we're interested in doing these confined chemical reactions in these local hotspots. So I will stop there and just thank my group. This was taken a couple of months ago when we were able to be in person for celebration of many thesis defense in person, even though they happened online. And I'll be happy to answer any questions you might have.
Thank you, Teri. Great presentation. So yeah, we have a few questions in the Q&A window. I'll go through those, and so people can add their questions there or raise your hand if you would like to ask your question verbally. So the first one there is from Suvankar, and this pertains to the use of annealing to reshape the nanoparticles. So you were using the annealing there to improve the shapes. I think the sort of essentially the roughness was decreased, or some imperfections in the shapes were decreased. And Suvankar is asking whether you can use the annealing conditions to control the shape of these particles, and whether you can control the optical properties that way, and is that desirable?
Yes, so we took structures that were sort of cylindrical, and the reason that they're not perfectly cylindrical is because we're depositing through a metal whole array film. And so because the metal whole array film also has grain structure, any of that grain structure, even though it's nanoscale, is going to translate into the masking of the particles. Okay, so that's just going to be a given. And I think it depends what types of properties you want to improve. So for example, if we want the narrowest SLR, and we know after annealing that we're going to have this dome-like shape, we need to start out with a much bigger particle than we would have ideally for the best SLR at that wavelength, because we're going to lose material. We're both going to lose material because we're annealing at like 900 or around there, and then also you're going to reshape. And so we designed the first pseudo-cylindrical structures such that after the annealing process, that particular hemispherical shape is ideal for the SLR. Mm-hmm.
And then could you perhaps change something like the wettability like by surface chemistry techniques, say, to change that shape? I guess it could go from being sort of more spherical to hemispherical by making them spread more or less during annealing?
I think that should be, I think it's governed by surface tension.
Yep.
So for the metals, so I don't think we can easily change that shape unless there was some quenching, artificial quenching involved. So these are deposited on quartz and not glass, just because we need, you know, transparent substrates that are robust to those high temperatures.
So I have a question that will fit in here well. That's related to the sort of tunability of your lattices. And my question pertains to using them to couple emitters to them, like say for the lasing work. And can you use the geometry to control the size of the hotspots? And do you have to trade off Q for the size? So say if you wanted to maximize the area covered by the hotspots and make them as big as possible, presumably you have some degree of control over there in the design. And then a follow-up question is whether you have to trade off. So if you want to make them larger, does that come at a cost of lower Q of the hotspots?
Okay, so let me just be clear about the SLR, how we get the SLR. So as I mentioned, it's the localized surface plasmon of the individual particle coupled to the lattice. So we cannot just arbitrarily change the localized surface plasmon properties to get that good SLR. So for example, say you have 100 nanometer particles on 400 nanometer spacing, and you have the perfect SLR. You know, something with a Q factor of say 500. That's mostly what we've had, invisible. If you just, if you change the particle's size, even though you keep the lattice the same, you're gonna detune the SLR because the wavelength of that localized surface plasmon is no longer at the optimized wavelength to couple to the diffraction mode to get the SLR at the wavelength that's mostly governed by the periodicity. So there's some trade-offs. There's some trade-offs there. And that can either be solved analytically or you can just screen using numerical or some other solver for those conditions. That's fairly straightforward. In terms of particle shape, I'm very excited about different particle shapes because I think there are different ways to break symmetry in these systems. And so, for example, even the rhombohedral, these diamond-like shape, that was a surprise to us that it worked like that. Actually, that the hot spots were in the same locations, but at very different wavelengths. And you sort of get that for free just by having asymmetric particle shape. So it's not like a rod, which has some type of symmetry too, but by having specific locations on the unit cell that can respond subtly to polarization effects, I think that will be really important for the next generation of, you know, just fundamentals of these types of lattices.
Okay, then that's a nice segue to John's question. He's got a question about those diamond-shaped nanoparticles. And his question is whether you used strain in that work to try and tune them. Presumably there would be way more sort of nuanced in terms of the response as a function of the direction of strain.
Oh yeah, so we could do that, but we didn't. So in the dual mode lasing using these rhombohedral type structures that are the diamond like nanoparticles, no, that was just on glass. So the only system that we've applied strain to was these more cylindrical particles.
Okay, then a question from Suvankar. What's the hydrogen yield in the hydrogen evolution reaction?
Oh, I don't remember, but it's terrible. I mean, it's not, I think it's fine. It's not, for this particular design, we were just mostly focusing on proof of principle. I don't think it's an optimized design yet for HER, but I would have to look it up. I don't remember it off the top of my head.
Okay, then there is one from Ken. I think you covered this, though let's see if you want to add anything to it. The nanoparticles as fabricated are not perfectly circular. Is this because of the shadow masking technique or the grain size of the metal? which you sort of spoke to at the start
Oh,
of the
okay.
Q&A. Yeah.
Yeah, I do think that it's more determined by the quality of the shadow mask. So we fabricate the shadow mask using our peel and stain process. So we have these, inch areas. But if you had a very, very nice shadow mask, I think you would have much, much, much better shapes of the metal.
Mm-hmm. Okay, then we have one from Dragomir. Can you please comment on the required sizes of the lattice arrays to achieve the high quality factors that you showed us, like the Qs of over 300?
Yeah, so we've done some calculations and that indicate at least that we can achieve lasing from a 30 by 30 system. Mm-hmm. So the SLR, it doesn't look good at 30 by 30, but the lasing looks quite nice. So I think we just need to go a little bit, okay. So the challenge is that we have basically almost an infinite array. So the excitation is much smaller than the size of the lattice. I think once the excitation size, so for example, say we patterned a 30 by 30, or even a little bit larger, I think what's going to happen is there are going to be edge effects. We can't avoid edge effects, and I think that will compromise some of the quality of the. I mean, I think it would be detrimental in some ways to the quality factor. This is what I think, but we haven't measured much except for 30 by 30, and I think it's this. We published it last year in ACS Photonics, and I mean, it's not. The lasing looks great, so that's the minimum required we needed for lasing. But the measurement, I think, is sort of, we'd have to use an objective to focus down the excitation source. But we could try it, because we can also send you some samples too.
Yeah. And a related question to that, and about sending samples. So say if copper was used for these structures where you're aiming for Q factors, like specifically, do those degrade with time rapidly, or do you like cap those, or to prevent the oxidation problem you mentioned? Because you mentioned briefly, I think, that you use them quickly after you fabricate them, or something to that effect.
Yeah, so the copper, there is some oxidation. I'm trying to remember whether we spent a long time analyzing the copper. We're working on this manuscript now. Let me look at that, and I'll get back to you, because we in the annealing paper, we mostly were trying to avoid the oxidation of copper, which is why the graphene growth was quite nice. But I can't remember how fast that it degrades. But I actually don't think it's that much if it's annealed. So let me put it that way. So if it's as fabricated, it's going to be rough, and the SLR is going to be, broad, 10, 15 nanometers full with that max. But once you anneal it with these dome-like shapes, I think the quality is still pretty good for a while, even though there will be a copper oxide. I don't think the SLR becomes horrible. We haven't seen the SLRs become horrible, even in the silver case. Which we know has an oxide too, which is a little bit surprising for us.
Okay, and then another question here. So this is no name, anonymous, and this one pertains to the photocatalysis work you showed right at the end. So the copper on platinum and platinum. So does the direction of illumination affect the plasmon modes? And specifically, does illumination through the quartz/ITO instead of through the photocatalyst make a difference? I
don't think it should make a difference. I mean, we've done this. I don't know that we tested it in the reversed case, but just in terms of the principle of reciprocity for optical properties, I don't expect it will make a difference.
Okay, that's the last one we have here. We have some Do we have some? Oh, so actually some people put questions into the chat. Let me just quickly see what's in here. So, a question on the white lacing with two kinds of face-to-face lattices. Is the generated white light coherent in this case?
Okay, so we didn't measure the coherence like we measured it in the other cases. I believe that the red light is coherent, the green light is coherent, and the blue light is coherent. If you superimpose all them together, does that mean that the white light is coherent? I'm not sure, but at least for the individual wavelengths separately within that white light emission, I believe those are coherent. But we have not measured in any sort of interference way, at least like we've done in the past, whether that white light emission that I showed you is coherent. I'm not sure.
Mm-hmm. Okay, and there is one more in the chat window here. So what is the typical output power from the plasmon nanoparticle lattice lasers?
Let me see. It's not high, meaning compared to the pump that we put in. I would need to go back and look at that because my brain is sort of filled with too many of these different laser systems, and it's really system dependent. So it will be different, for example, in the dye case versus the quantum dot case versus the upconversion nanoparticle case. But I'll find that out and get back to you on that.
Mm-hmm. Okay. And I'm not seeing any other ones here. So yeah, I think that's the end of the questions. Nobody's raised their hand. No. Okay, so thank you once again, Teri. That was fantastic. And
yeah, thanks for having me, and I look forward to more discussions, sending samples, sending students, things, exchange. That's sort of why we have this program, which, well, we'll get there. We'll get there.
Yep. Well, yeah, we all got a bit derailed in the last couple of years.
Yeah.
Yeah.
Indeed.
Okay, fantastic. Thank you again, and
okay,
have a good evening.
thank you very much. Have a good day, everyone. Bye-bye.
Bye.